Hello there, Mr. Sutton with the AB Calculus 613 Extra Practice number 1 answers on volume with solids of revolution. On this problem, we're trying to find the volume when we take the area between y equals x and y equals x squared and revolve it around the x-axis. Let's start by graphing this out. So I've entered these as y1 and y2 on my calculator, and I'm going to do zoom, let's do zoom 4. I'm pretty sure these are going to intersect close to the origin, and they do. At the origin and at, well, this looks like it's about 1. If you were to zoom in, you would see that it is indeed. And you could do second trace and intersect. But, I mean, if you just set x equal to x squared, this clearly happens at 0 and 1. 1 equals 1 squared. So 0 and 1, then, are going to be our limits of integration for this area revolved around the x-axis. Next, we need to find the actual area of the cross-sections. Now, since there's a gap between the area that you're revolving and the axis of revolution, there's this space in here. Our model that we're using is going to be donuts, washers. Our cross-section is going to be given by the formula pi times big R squared minus little r squared. Big R squared, that's the part of the area that's further away from the axis of revolution. That's this top function here, minus the axis. So this is just going to be x then that we're squaring for the big R squared. And then for little r squared, that's the part of the area closer to the axis of revolution. So that's going to be x squared minus 0, or just simply x squared. But we're also squaring x squared, so be careful with all those squareds. All right, now it's time to put this in my calculator. So I have the integral from 0 to 1. This is going to give me the volume. Integrating the area formula, a of x dx. And let me put this on the calculator now. Just in the name of being careful, I'm going to put this area formula in my y3 so I can get a very good look at what I'm actually doing in here. And then I'm going to quit out of there and integrate from 0 to 1. And I'll do alpha trace y3 now, dx. And that'll integrate my area formula. So pressing enter, I get about 0.419 if I round that off. And that's my volume. On this problem, we want to rotate the area between x squared and y equals 4 around the line y equals 4. Well, this will be interesting. Let's graph this out and see what we're dealing with. So here's my functions I've entered in my y equals. Let me just do zoom 6, get a wider view of what I'm doing here. And I could probably zoom in a little bit if I wanted to, but that's the essence of what we're dealing with. So we have this region in between y equals 4 and x squared, and we're revolving this around the line y equals 4, which we've already drawn here, but I'm just going to draw a red dashed line. If you can see it there, just to show us that's what we're revolving around. So let's find the intersections here, because that's going to give us our limits of integration. We can see that x squared equals 4. Where? I mean, I could look this up on the calculator, but if we square root here, this is just going to be plus or minus 2. So I have an integral from negative to positive 2. An integral of what? Now I need my area formula for the cross-sections. So taking a look at my bounded region here, when I revolve this, there's no space between my bounded area and my axis of revolution. So that means that I'm going to have solid circles as my cross-section. I'm going to have disks. So I can use the area a of x equals pi r squared formula for my cross-sections. In this case, r is just this x squared here. Well, it's almost x squared. It's the distance between my axis of revolution and my other bounding function. So that's actually going to be a distance of 4 minus x squared that I have to plug in for r. And now I'm going to go to the calculator, but let me show you the setup that I'm putting on my calculator. So my volume is going to be the integral from negative to positive 2 of this a of x that I just came up with, dx. All right, here we go. To make things a little bit easier, I'm going to go to my y equals and actually put my area formula in the y equals. So let me do second exponent button gives me pi, and then in here I'm going to have 4 minus and just x squared, so I can just write x squared or y1, either way. And now I have to square this whole parentheses. And now let me quit out and actually take the integral. So that'll be math 9, integral from negative 2 to positive 2 of alpha trace y3, that's where I just put that area formula, dx, and that comes out to 107.233. On this no calculator problem, I'm trying to revolve the area between square root of sine of x, y equals 0, in other words, the x-axis, and x equals 0 and x equals pi, about the x-axis. So for this one, they've basically already given me my limits of integration, 0 and pi. That's just the two vertical lines that this area here is bounded between. So now I just need to find the area of the cross sections and integrate that from 0 to pi. All right, well, my area of my bounded region here, the area under square root of sine of x right here, this is flush against the x-axis. There's no gaps, so we can use discs on this one. So I'm going to say a of x equals pi r squared, where r in this case is the distance between this function and the x-axis. So that's just pi times the square root of sine of x squared. And you can probably see why this is a no calculator question, because this is really just pi times sine of x. So let's go ahead now and integrate this from 0 to pi. So my volume is the integral from 0 to pi of pi times sine of x dx. Antiderivative of this, that's going to be negative pi times cosine of x. And we're doing that from 0 to pi. I'm going to yank this negative pi out of here. So inside now I just have cosine of pi minus cosine of 0. Cosine of pi is negative 1, and we're subtracting the cosine of 0. Cosine of 0 is 1, but we're subtracting it. So this is negative pi times negative 1 minus 1. Negative pi times negative 2 comes out to 2 pi. For this problem, we have R as the region in the first quadrant bounded by 8 minus x to the 3 halves, the x and the y-axis. First part of the problem, we're just trying to find the area of R. So this is a grapher problem. I'm going to start by graphing this thing to see what I'm dealing with. And they did say that this was in the first quadrant. So for my window, I'm going to start at 0, and I don't know how far out I'm going. Let me just go out to, I don't know, 10. We'll see. And then let's just do a zoom fit on that. Zoom 0. See how this works out for us. Okay, so it looks like we're just bounded in this region right here. I'm actually going to zoom in a little bit. Let me just change my y min to be, I don't know, negative. Well, how about just 0, right? All right. So here's a slightly better picture of what we're dealing with. Now, in order to find this area, I need limits of integration. So clearly we start at 0 because we're bounded by the y-axis. But where are we intersecting the x-axis? It looks like 4, but I'm not really sure. So I'm going to find that on the calculator too. Before I do that, though, just showing my work here, I'm going to rename this function to just be f of x so I don't have to keep writing it out. And I'm going to set this equal to 0 and solve on the calculator. So on the calculator, I'm going to do second trace, option 2, zeros. And my left bound, let's see, where's my spider? There he is. All right, so there's the left bound. Let me click a little bit to the right of that. And then I'll guess. And let's see what we got. Oh, it's exactly 4. Okay, well, now we know. It looked like 4, but I mean, sometimes it's a little bit off, and you want to be accurate. So now we need to find an integral from 0 to 4 of top minus bottom. So that's just going to be f of x minus 0, or just f of x. So integral from 0 to 4, f of x dx, and it's calculator time again. So here's what this looks like on the calculator. I did math 9 to get my integral, 0 and 4 my limits, and y1, again, that's where I stored my f of x function. So pressing enter here, this is going to come out to about 19.20000 and some change. So we'll round it off to that. For this part of the problem, I want the volume of the solid when r here is revolved around the x-axis. So I have the same limits of integration as the area from 0 to 4. But now for the thing that I'm integrating, well, I'm going to have to get the cross-section area here. Since the bounded region has no gaps between it and the axis of revolution, it's flush against the x-axis here, that means I can use discs or pancakes for my area cross-section. So I'm going to write a of x equals pi r squared, and r is just the distance of this bounded region edge here to the axis of revolution. So that's just a distance of whatever this function is, f of x. So I'm just going to write pi times f of x squared. And now this is what I'm about to integrate. Now when I do this, normally I won't do this, but I'm going to call my volume v. And on my calculator, once I find this, I'm actually going to store this value as v. Normally I wouldn't bother, but this is not the end of v for this problem. I've read ahead a little bit, and I see that in part C of this free response, I'm going to need whatever value I get for v. So since I read ahead, I'm going to store it while I'm doing this part of the problem. All right then, so I'm going to have an integral from 0 to 4 of this a of x dx. And now for the calculator. So here's what this looks like on my calculator. Integral from 0 to 4, pi times f of x is really just y1 on my calculator, so y1 squared, dx, and that's going to come out to how much? 361.911 and some change here. So I'm immediately going to store that as a letter, and v is the one that I'm going to pick because that is the volume. So I'm going to do alpha v right there. And now I can bring it back and use it whenever I want. Okay, so let me just write it down officially here so I get some credit for it. And it's time to move on to the next part. For this next part of the problem, they're telling us the vertical line x equals k divides the region R into two regions such that when they're revolved around the x-axis, they give us solids of equal volumes. We want the k value that does this. So just to get a visual here, we're putting a vertical line somewhere in this bounded region, and when we cut it up in just such a fashion, we get volumes that are the same when we revolve this. So we need to figure out what k is, and they tell us that so if we get equal volumes, here's the key on this one, that means each of these volumes that we should get out of this process should be half of this v value that we just found here on part B. So what I'm going to do is I'm going to take the integral from 0 to k, there's some k value, that when I integrate my area formula, which if I write it out again is pi times f of x squared, or I'm actually going to write it out on this one, 8 minus x to the 3 halves squared dx, and you'll see why I'm doing this in a second. If we do this, we should get a volume that is half of v. So I'm going to say that this equals v over 2. Okay, so where do I go from here? Although this is a calculator problem, there's actually a large part of this that you need to do without a calculator, at least to get credit for showing your work. I'm actually going to have to use my fundamental theorem on this integral and get an expression that has a bunch of k's in it so that I can use that to solve this equation. So let me start with first things first, making my life a little bit easier in terms of taking the antiderivative. I'm going to start by pulling pi outside the integral. No need to keep that hanging around in there. And in here, I'm going to expand this. So square the first thing. That's going to be 64. And then multiply these together and double it for the minus 2ab part of my squared binomial shortcut. So this is going to be negative 16. And let's see here. X to the 3 halves. Yep. And then finally, I have to square this last thing. So we're just multiplying this exponent by 2, essentially. So 3 over 2 times 2, the 2's cancel. So that's just x to the 3rd, and that's going to be positive. And don't forget the dx. And again, all of this, when I do it correctly, should equal v over 2. All right, time to take my antiderivative, because I didn't actually do that yet. I just simplified the integrand. So 64, that's going to be 64x. And I still have this pi hanging around out here. And let's see, this one is going to be, I bumped this up to a 5 over 2, multiply by 2/5. That's going to be 32 over 5, x to the 5 halves. And then this last one, this goes up to the 4th power. Dividing by that, we have plus 1/4, x to the 4th, all evaluated from 0 to k. And again, this equals v over 2. Don't lose your equation. All right, time to actually plug in k and 0. Now, before I do that, since this is an equation, I can actually get rid of this pi out in front by dividing both sides by it. So over on the right side, I'm just going to have v over 2 pi. And now let me see what I've got on the left side. So I've got all of this stuff with k plugged in. So basically just replace x with k. Minus all of this stuff with 0 plugged in. But here's the nice part on this problem. If you plug 0 into all of these things, they all just get zeroed out. So really, it's just these expressions with k that we have to worry about. Now, if you're wondering how you're possibly going to solve this algebraically, the answer is you're not. You're going to actually graph this out on the grapher and see where it intersects this line here and go from there. So here I am in my y equals. I got rid of this original f of x because this is the last part of the problem and I'm not going to need it again. I entered this expression that has k's in it, the left side of my equation, as y1. Notice that I used x's instead of k's because your calculator just considers k a constant. X is really the only variable it knows how to graph. Now let me go down to y2. This is where I'm going to put the second half of the equation. So I'm going to do alpha y equals for my fancy fraction here. In the numerator, I've got v, which I already stored in part b of this problem. So alpha v, I'm going to pull that back there. And down in my denominator, I need 2 pi. So here we go, 2 times pi. Now the nice thing about doing fancy fraction on this is that it takes care of PEMDAS. If you just did v divided by 2 times pi and you didn't put a parentheses around 2 and pi, then you'd be in trouble. But this fraction formatting, the calculator figures out that both of these things belong downstairs. All right, so where do we intersect on this? I have no idea, but I know it's going to be somewhere between, hopefully, 0 and 4, because 4 was our limit of integration when we found the area and revolved the whole thing. So let me go to my window, and I'm going to make this 0 to 4. And let me do zoom fit now so I can get a good picture of where these things actually cross. All right, so here is my polynomial-ish sort of wannabe thing involving those k's. And here is that second half of the equation, v over 2 pi. What is this intersection spot? Well, let's do second trace, option 5, intersect, to actually figure that out. So moving my spider a little bit closer just to save time when it actually calculates. Enter 1, 2, 3 times, and we get a value of 0.995. So there it is. That's the end of this problem. Hey, we just found k. For this problem, we're given this shaded region S in our first quadrant, below the line y equals 3, and also bounded by y equals 3 sine of x. And on the left, this is kind of interesting, we have this vertical line x equals k. We don't know what k is, except that it's somewhere between 0 and pi over 2. So we want to find the area of S when k equals pi over 3. That's our first task here. Okay, well, I need to find my limits of integration here. I'm going to just be integrating a distance strip that has the format top minus bottom, but before I can do that, I need my limits of integration. So I don't know what my k value, well, actually, I know what my k value is. It's pi over 3 for this particular piece of the problem. So we need to find the right limit of integration now. I have a strong suspicion it's pi over 2. Why else would they limit k to being between those values? But I'm not going to assume anything. Let's actually solve for the x value over here. So I'm going to write, let's see, 3 sine of x equals 3. I want to know where this thing equals 3. And if I divide by 3, I've got sine of x equals 1. And then inverse sine, I'm going to get pi over 2. I get a lot of other things as well, but pi over 2 is the first one I get. So we're going to stick with that. So it does end up being pi over 2. I have the integral then from pi over 3 to pi over 2 of what? Well, I need to do top minus bottom. So that's going to be 3 minus my lower function, which happens to be 3 sine of x. And don't forget your dx there. Okay, this is a no calculator problem, so we have to do this by hand. Antiderivative time. 3 is going to become 3x. And then negative 3 sine of x, that's going to be positive 3 cosine of x. All this evaluated from pi over 3 to pi over 2. So I have all this stuff with pi over 2 plugged in. And I'll pull a 3, I'm going to factor a 3 actually out of here. So I'm just going to have like x plus cosine of x inside. So I'm going to have then pi over 2 plus cosine of pi over 2 minus pi over 3 plus cosine of pi over 3. So if this is a real AP free response problem that I'm doing, I mean, it is, but if I'm actually doing this for real on the exam, I'm stopping here. These are all constants. So I've done my job. I've gotten it down to constant land, and I can move on. But just for the sake of simplifying in practice, I'll go ahead and do the rest of this. But again, keep in mind you do not need to simplify past this point. So going from left to right here, I still have 3 on the outside. I've got a pi over 2. I've got cosine of pi over 2, which is really just 0, so I can just ignore that. Over here, I've got minus pi over 3. And then cosine of pi over 3, I'm converting this to degrees because I can't think in radians. This is really cosine of 60, which I know is 1/2. We have a minus out here, though, so this is minus 1/2. And now combining like terms in here, a common denominator would be 6. So I've got, this is 3 pi over 6 minus 2 pi over 6. So that's just pi over 6 minus 3 over 6. So that'll be pi minus 3 over 6 then, if we combine everything together. And then this 3 and this 6 are going to reduce to give us just pi minus 3 over 2. Again, though, you could have stopped right up here. On this problem, they're telling us the area of S is a function of k, and then they want the rate of change of S with respect to k when k is pi over 6. So we first need to write out an S function with k as the input variable, and then take the derivative and plug in pi over 6 for k. That's our game plan on this one. So S of k, the area of S, that's going to be an integral. It's going to be an integral from whatever k is right here to pi over 2. So we can start there. We need an integrand, though, and we actually kind of did this on the last problem. It's just top minus bottom. So 3 minus 3 sine of x dx. And this is what we're going to try taking the derivative of now. Sort of. We're almost set up to make our lives super easy because we have a variable in one of the limits of integration. But before we can go ahead and just take the derivative and plug k in here, we need k to be in the upper limit of integration. That's how the fundamental theorem works. You have a variable in the upper limit. So to get k in the upper limit rather than the lower limit, we're going to switch the limits of integration. And we're going to do that using one of our definite integral rules, where you can just negate the whole integral, and that effectively switches your limits of integration. It's kind of like integrating backwards. So I'm going to rewrite this as negative integral from pi over 2 to k of 3 minus 3 sine of x dx. Now I'm set to go ahead and take the derivative of this integral. So I can write that s prime of k on the left equals, I'm still going to have this negative. Now I'm just going to plug k in for my dummy variable x, and I have 3 minus 3 sine of x inside that parentheses with that negative outside. And if there was more to this than just k, if this was a function with a tail that was something other than 1, I'd multiply by that as well using fundamental theorem. But it's just k, so we just plug in k. All right, at this point I'm ready to go ahead and actually plug in pi over 6 for my k value right here. And I'm going to distribute this negative 2 just to get that over with. So this is negative 3 plus 3 sine of pi over 6. Sine of pi over 6 is 1/2. That's just the sine of 30. So this is negative 3 plus 3/2. And you actually could have stopped right here. You didn't even need to simplify sine of pi over 6. But if we take it all the way, this ends up being negative 3/2. For this part of the problem, they're telling us region S is revolved around the horizontal line y equals 5 to form a solid. Write but don't evaluate, that's my favorite expression. Write but don't evaluate an expression with some integrals to give us the volume of a solid when k equals pi over 4. All right, so let me start by drawing my line here, y equals 5. Not really drawn to scale, but it's up there somewhere. So we need to revolve S around this line. Now, because there is a big old space here between my bounded region and my axis of revolution, that means I need to use washers in order to figure this out. So I'm going to write a of x equals pi times big R squared minus little r squared. Doesn't give me any credit, but it gives me a nice little format to plug things into. My outer radius, that's the part of my bounded region that's farther away from my axis of revolution, or at least the distance from the axis of revolution to that furthest part. That's going to be 5 minus this function down here, 5 minus 3 sine of x. So I'll have pi, parentheses, 5 minus 3 sine of x, quantity squared. That's big R squared. For little r squared, I'm going to have the distance from the closest part of my bounded region to the axis of revolution. So that's going to be 5 minus 3 to get this little distance in here. And we have to square that as well and subtract all that. Now, the nice thing about this is they said write but don't evaluate. So I don't even need to plug this in the calculator or anything like that. I just need to write an integral that has this in it. So my integral, my limits of integration, we're going to be going from k equals pi over 4, because that's what they told us right here, to pi over 2. And then in here, I'm just going to have this a of x that I just came up with a dx next to it. And I'm actually done.